Hello, good afternoon, everyone. Kelvin Wahome, how are you?
I'm very fine, madam.
Who else? Joram, how are you doing?
I'm fine, man.
Okay, so as I always say, we don't have the luxury of time. The rest will catch up along the way. So last time we looked at random variables, whereby we talked about two types of random variables. We talked about the continuous random variables. Then we also talked about the discrete random variables, whereby for the discrete ones, we said these are the kind of random variables whereby they're countable and they're finite, whereas the continuous random variables, they take values within a given specified range of values or an interval. So with that, I want us to look at the different kinds of probability distributions that we might come up depending on the type of variable that you're dealing with. So when it comes to probability distributions, what happens is if you perform a given experiment, we are still talking about probability. If you perform different experiments, the outcomes that you record end up following a given distribution. For instance, if I toss a coin, say 10 times, and I record the different outcomes after tossing this coin, that probability distribution, or what you are calling the PMF for a discrete random variable, ends up with different kinds of distributions that you want to look at. So when it comes to probability distribution, we also have what you refer to as the discrete distributions. So we have the discrete distributions. Then we also have what you refer to as the continuous distributions. We also have the continuous distributions. So generally, when it comes to statistics, there's so many distributions. For instance, when you talk about discrete, there's some distributions. For instance, you have what you refer to as a Bernoulli distribution. We have the binomial distribution. We have another one referred to as the Poisson. We have another one called the geometric. Then there's also hypergeometric, and so on and so forth. So these are the different kinds of distributions that a random variable might follow. But for our scope of study, when it comes to the discrete distributions, we'll focus on the Bernoulli. We'll focus on the Bernoulli, binomial, as well as the Poisson. So Bernoulli and the binomial are kind of related. We'll see that in just a minute. Then we'll also look at the Poisson distribution. Then when it comes to continuous distribution, same case. For continuous distributions, we have the most common distribution that we use. The normal distribution is the widely used distribution in statistics, which is the one we'll look at. We have what we refer to as the uniform distribution. We have the exponential distribution, and so on and so forth. So for the continuous distribution, our focus is going to be on the normal distribution. So we'll look at these ones for today's lesson. I want us to start with the discrete distributions. And the first distribution is what we refer to as the Bernoulli distribution. We have the Bernoulli distribution. So what this distribution does, let me just project. For the Bernoulli distribution, this is the kind of distribution that caters for outcomes that can only take two values. It's either your outcome is a success or a failure. So when it comes to Bernoulli distribution, when you perform a given random experiment that has only two possible outcomes, so it's either a success or a failure. Such a random experiment is what you refer to as a Bernoulli trial. So for instance, with the tossing of the coins, We've talked about tossing a coin so many times, and we came to the conclusion that if you toss a coin, it's either the coin lands on a head or a tail. So that's what you talk about, only two possible outcomes. Same with producing certain items in a machinery plant or in a factory. If you decide to produce a light bulb, it's either the bulb is not defective. So if the bulb works properly, that's a success. If the bulb does not work, then we refer to that as a defective bulb, which is equivalent to a what? A failure. So for Bernoulli distributions, any kind of experiment, which you're saying we refer to it as a Bernoulli trial, has only two possible outcomes: an outcome of either 0, which is a failure, or an outcome of 1, which is what you refer to as a success. So when it comes to this distribution, just before we continue with the Bernoulli distribution, we'll focus on these particular items. When you talk about Bernoulli, binomial, Poisson, as well as the uniform, the normal distribution, we want to understand the following. We want to understand the definition, just the layman definition of what this kind of distribution is. Then after we define it, we look at its particular formula. So for the formula, if it's a discrete distribution, we talk about the PMF, whereas if it's a continuous distribution, we'll talk about the PDF. So we mentioned these terms when we were talking about random variables during our last class. So we look at the formula. Then after the formula, we look at how we notate. So we look at the notation for these particular distributions. Then finally, we look at the mean as well as the variance. So these are the points you're going to be focusing on as we describe these distributions. So back to Bernoulli. For Bernoulli, we've already explained that this is that distribution whereby for any given trial, you only have two possible outcomes, success or a failure. So when it comes to the notation, the PDF, so that's the definition, the PDF, which is the formula for the Bernoulli distribution, is given as follows. First of all, the probability of a success, the probability of obtaining a success is equals to a value of P, whereas the probability of a failure is equals to a value of 1 minus P. Why are we saying this? One of our rules of probability was that the summation of any given probabilities is always equal to a value of 0. And since you're saying for Bernoulli, we only have two possible outcomes. If one outcome, which is a success, is equal to a value of P, then the other one, which is the probability of a failure, is going to be equal to 1 minus P. So if we have these two notations, then the PMF for a Bernoulli distribution will look as follows. So we'll have the probability that a random variable follows a Bernoulli distribution is equals to the following. So this is the formula. We'll have P raised to the power of X multiplied by 1 minus P raised to the power of 1 minus X. Of course, you say the values of X can only take two values, either a 0 for failure or a 1 for success. Anything else gives us a 0, so 0 otherwise. So this is the formula for Bernoulli distribution. P, we've said, represents the probability of success. X is either 0 or 1. Then 1 minus P is the probability of failure. So that's the formula we'll be using. Then when it comes to the notation, if a given random variable X follows a Bernoulli distribution, we represent it as follows. We say that X follows a Bernoulli distribution. So Bernoulli is denoted by capital B. Then what you write in brackets is the parameter in question. The parameter in question here is the probability P. Let me just take you back to what a parameter is. When you're talking about numerical summaries, we said that when you're dealing with a sample, the summaries that you end up with is what you refer to as a statistic. Whereas when you're dealing with the population, the summaries you end up with is what you're referring to as a parameter. So a parameter is just an unknown variable that will still be in a position to compute. So the notation for a Bernoulli distribution is as follows. When it comes to reading this, we read it as follows. We say that the random variable x follows a Bernoulli distribution with parameter p. Or you can simply just write it in full and say that random variable x, follows a Bernoulli distribution with parameter p. So that's how we notate it. Then when it comes to the mean and the variance, the mean of a Bernoulli distribution, so mean we say it is denoted for a random variable is denoted by mu. So mu is equals to p, whereas the variance is equals to n multiplied, whereas the variance for a Bernoulli is equals to p multiplied by 1 minus p. So for instance, if you toss a coin, if you toss an unbiased coin, it's either it lands on a head or a tail. So the probability of it landing on a head, let's say the probability of it landing on a head is a success. So the probability of it landing on a head will be equal to a half. Then the probability of it being a failure on landing on a tail is also going to be a half. So the mean for a Bernoulli distribution, you're saying it's equal to the value of p. So if you had such a random experiment, then here the mean of this will be equal to the same value of p, which is equals to a half, and the variance will be equal to p multiplied by 1 minus p to give you 1/4. So that's the formula for the mean. It's simply the probability of success, whereas for the variance, you'll have p multiplied by 1 minus p. So that this gives us the basic for a Bernoulli distribution. Like I said, our focus is on the binomial distribution, but for us to get into this, we need to understand what a Bernoulli distribution is. So you basically have one independent trial that has two possible outcomes, a success or a failure. Now, with that background information, we should be in a position now to explain what a binomial distribution is. When you go back to a binomial distribution, I hope I can clear the whiteboard. When you go back to a binomial distribution, we define this as follows. Let's talk about a binomial distribution. So this is the relation between the binomial and the Bernoulli. So for a binomial distribution, a trial still has two possible outcomes, either a success or a failure. But a binomial distribution in this case is a sequence of n independent Bernoulli trials. So we can say that, let's say, consider a sequence of n independent, actually you can just say this is a sequence. This is a sequence of n independent Bernoulli trials, n independent Bernoulli trials, with each trial having two possible outcomes. With each trial having two possible outcomes. So that is still either a success or a failure. A success or a failure. So what are we saying? If I just toss a coin once and I record my outcomes, we refer to that as one independent Bernoulli trials. But for instance, if I say, let me toss this coin 10 times and record this outcome. So you see, the value of n in that example will be a value of 10. So when it comes to a binomial distribution, this is just a sequence of n independent Bernoulli trials. Same thing with the example you give about the bulb in a machinery plant. Like if you decide to observe whether a bulb is working after production, if you just observe that one bulb, we refer to it as a Bernoulli distribution. But if you decide to observe a box of 100 bulbs to determine whether they are working or not, we refer to that as a binomial distribution, because a bulb is either working or is not. So there's only two outcomes. It's a success, which is a value of 1, or it's a failure, which is a value of 0. So this is why we're saying the Bernoulli and the binomial distribution are related in this manner. So this is just a sequence. So that's the definition bit of it. Then you can look at its particular formula. So since the binomial distribution is still a discrete kind of distribution, we refer to its formula as a PMF. So the PMF of the binomial distribution is given as follows. So the probability of random variable X will be given by the following formula. We'll have N combination X multiplied by P raised to the power of X multiplied by 1 minus P raised to the power of N minus X. And of course, in this case, since you're saying for a binomial distribution, these are multiple trials, X can take values from 0, 1, 2, all the way to N. So X here will take values from 0, 1, 2, all the way to N. So just from this formula, you can still see the relationship that exists with the Bernoulli. Remember, for the Bernoulli, how did you give our formula? Our formula was as follows. We had P to the power of X, then into 1 minus P to the power of 1 minus X. So look at the difference. P to the power of X is still the same, 1 minus P is still the same. But when it comes to the power, for the Bernoulli, we were talking about 1 minus X, because we were talking about one independent trial. But when it comes to the binomial distribution, we are talking about N minus X, where N now represents the total number of trials. Then we also include this combination bit. So what this combination does is it basically counts the number of outcomes. It counts the total number of outcomes, whether it's a success or whether it's a failure. So that is why we put it at this point. So this is our formula for the PMF of a binomial distribution. Then with that, we said after the formula, we look at the notation. So how do we notate a binomial distribution? The notation will look as follows. So we say that X, random variable X, follows a binomial distribution. So we'll have random variable X follows a binomial distribution with parameters N and P. With parameters N and P, or alternatively, we can just write it in full. So we can say X follows a binomial distribution, and the parameters are either N or P. So this means the parameters in question, our unknown values here. We'll need to find the value of N, which is the number of trials. Of course, X represents the probability in question, whereas P represents the probability of a success of a given experiment. So this is the notation. Then when it comes to the mean for a Bernoulli, the mean for a binomial distribution is given by mu is equals to N multiplied by P. And then the variance is given by this. The variance will be given by N multiplied by P into 1 minus P. N multiplied by P into 1 minus P. Now, the reason you're talking about the mean and the variance as well is because in some problems, when you're working out the solutions, some problems you might be given the probability of success, but in others, you might find that you're given for instance, you're given the value of the mean, And you also have the number of observations. So yours is to remember, for me to get this particular probability, I know that the mean is equals to n multiplied by p. So if I have the mean already as 10, and I have the number of observations already as 5, then I can easily compute my value of p. Alternatively, you can be asked to compute the mean or variance of a given binomial distribution. So yours is to just use these particular formulas to give you the required solutions. So with those basics, let's look at an example. Let's look at an example of binomial distribution question. For example, I hope I can get rid of this. So we work on an example together. So an example, you're told that a biased coin is tossed 6 times. A biased coin is tossed 6 times. The probability of heads on any toss is 0.3. Then you're told let x denote the number of heads. Let x denote the number of heads that come up. So you're told to calculate 1, the probability that x will be equal to 2. 2, the probability that x will be equal to 3. And 3, the probability that x will fall over the interval from 1 all the way to 5. So we want to compute these probabilities. Let's understand the question. We are told that a biased coin is tossed 6 times. The probability of heads on any toss is equals to 0.3. Then let x denote the number of heads that come up. Let me just say why are we calling it a biased coin? Because for an unbiased coin, if you toss a coin, it's either it lands on a head, on a tail, a head or a tail with equal probabilities. Probability for a head will be 0.5 and probability for a tail will also be 0.5. But if we talk about a biased coin, that means that the head or the tail don't have equal probabilities. You know, there's usually those coins whereby, have you ever let's say you're given change from a supermarket or whatever, you have the coin, then you see it has some dents because it looks super old or whatever, but it's still a coin. So that's such an example of a biased coin. It's not given that the probability for a head or a tail is 0.5. So this is why they're clarifying that this coin is unbiased. And this is why we see that they're saying the probability of it landing on a head is equals to 0.3, as opposed to the usual 0.5. Then we're told that let x denote the number of heads that come up. Calculate the probability that 1, x is equals to 2. So how do you denote this? The first step for you is to determine the kind of distribution you're dealing with in a question. A question like this, we are talking about tossing a coin, and you can only have 2 outcomes. It's either a head or a tail. So that already tells us it's a Bernoulli or a binomial distribution. Then after that, what other information do we have? We are tossing it 6 times. So that means our n independent trials is equals to a value of 6. So that automatically means that you're dealing with a binomial distribution. So with these questions, it's important for you to be able to determine whether it's binomial, whether it's Poisson, or whether it's a normal distribution. So luckily for us, we're only dealing with these 3. So it's going to be really easy to differentiate. So for this particular question, of course, you're dealing with a binomial distribution. So if you're dealing with a binomial distribution, that means that we know very well the formula for a binomial distribution is given by what? Is given by n combination x multiplied by p raised to the power of x multiplied by 1 minus p raised to the power of n minus x. So you want to compute the probability that x will be equal to 2. How do we go about this? Let's find all our unknown values. In this case, our value of n, we need n, x, and p. What's our value for n? N are the number of independent trials, so n is equals to a value of 6. Then what about the value of x? We want to determine the probability that the probability of x is equals to 2. So my value of x is going to be a value of 2. Then what about my value of p? P we said is the probability of success. And you're saying that let x denote the number of heads that come up. So the probability of it landing on a head is our success in this particular instance. So P is equals to a value of 0.3. So all that is left for us is to get this probability. So this will be equal to 6 combination 2 multiplied by P. Let me just use the multiplication sign. So a dot and a multiplication sign are one and the same thing. So 6 combination 2 multiplied by P, which is a value of 0.3 raised to power x, which is a value of 2, then multiplied by 1 minus P. So 1 minus P is 1 minus 0.3, which is equals to 0.7. So we'll have times 0.7 raised to the power of n minus x. N minus x is 6 minus 2 to give us a value of 4. So all that is left is to compute this from our calculators. I hope we know how to compute 6 combination 2. So take 6 combination 2 times 0.3 squared times 0.7 raised to the power of 4. So this will give you a probability of 0.3241. So that is going to be a probability that x will be equal to 2. Are we together? Boniface, Kirago, am I making sense? Boniface, are you with us today?
Yes.
Okay. So that's how you compute the probability that x is equals to 2. What about the probability that x is equals to 3? So I think we do the same thing. What changes? Our value of n is still equals to 6. Our value of x in this case now is a value of 3. Our value of p is still equal to 0.3. So to compute this probability, we'll have n combination x. So 6 combination 3 multiplied by p, which is 0.3 raised to power x, so 0.3 raised to power 3, then multiplied by 0.7 raised to power n minus x. So raised to power 6 minus 3, which is a value of 3. So again, you can get this value from the calculator to get 0.1852. So that gives you the value for that particular question. Then number 3, you want to compute the probability that the value of x lies within this interval. So again, remember we are talking about a binomial distribution, which is a discrete kind of distribution. And we said for the discrete distribution, we are dealing with countable, we're dealing with countable values. So for this interval, we said, how can we represent this? For us to guess the probability from 1 all the way to less than or equal to 5, this is still the same as talking about the probability that x is equals to 2, plus the probability that x is equals to 3, plus the probability that x is equals to 4, plus the probability that x is equals to 5. Because for the discrete random variables, we're talking about different integers. So for this range, we are starting at 2 rather than 1, because we are following our less than sign here. So here we have only less than, we don't have the equal to sign here. That's why we're ignoring x is equals to 1. Then we begin from x is equals to 2, 3, 4, as well as 5. So 5 is also inclusive of the interval because we have the equal sign. Then with that, all that is left is to guess these respective probabilities. So this will equal to what? We have the probability that x is equals to 2. We computed it here. We have the probability of x equals to 3. We computed it there. So we are left with computing the probability of x is equals to 4 and the probability of x is equals to 5. So let's get these values. We'll have 6 combination 4, then into p, which is 0.3 raised to the power of x. So my x there is 4, multiplied by 1 minus p, which is 0.7 raised to the power of n minus x. So 6 minus 4 to give you 2. So what do you get for that? 6 combination 4 plus, 6 combination 4 multiplied by 0.3 raised to the power of 4 multiplied by 0.7 squared. I have here 0.059. Then for 5, we do the same. So we'll have 6 combination 5 into 0.3 raised to power 5 multiplied by 0.7 raised to power 6 minus 5, which is equals to 1. So this other one will give me, I don't have that value. Give me this value for the last one. Someone give me that value kindly. If you have it, kindly type it out for me along the chat box. The value for probability of x is equals to 5. Zero 0.0102. Okay, so with that, you can guess the total probabilities now. So we'll add up 0.3241, 0.3241 plus 0.1852 plus 0.059 plus 0.0102. So this will give you that probability for that interval. What do we get? 18.52 plus 0.059 plus 0.0102. So I have 0.5785. So this is the probability. That's the probability that random variable x, which is the number of heads, falls between 1 all the way to 5. So this means you're getting the probability that since we are talking about 6 tosses, this range means that out of the 6 tosses, we want the probability that you'll get 2 heads, or you'll get 3 heads, or you'll get 4 heads, or you'll get 5 heads. So this will depend on the interval. What about if you were looking for the probability that x is greater than 3? How do we go about that? Probability that x is greater than 3. So you need to understand what random variable x means. In this particular experiment, x is the number of heads that will come up. And remember, the coin is being tossed 6 times. So the head, if you're tossing it 6 times, that means it can land on a head once, it can land on a head twice, thrice, 4 times, 5 times, 5 times, or 6 times. So with that, how can you guess the probability that x is greater than 3? So the maximum we can have is a value of 6, since you're only tossing it 6 times. So the maximum number of heads you can have is 6. So to get the probability that x is greater than 3, we can look at it in 2 different ways. We can look at the probability that x will be equal to 4, the probability that x is equals to 5, or the probability that x is equals to 6. The other way we can look at it is by saying this: the probability that x is greater than 3 is also the same as saying 1 minus the probability that x is less than or equal to 3. So if you compute this and this, you should get the same answer. Because again, we are talking about a maximum of 6. That's why we've gone from 4, 5, 6. The other way around, you can have 1 minus, because you know the total probability will always be equal to 1. Or the other way, we can take 1 minus the probability that x is less than or equal to 3. So you'll still use the same formula, same formula for the binomial distribution. Add up for 3, 4, 5, and 6, or compute for x being less than or equal to 3, then subtract it from 1. Then you get your answer. Any question on the binomial distribution? So the other kind of distribution is what we referred to as the Poisson distribution. I want us to look at the Poisson distribution. So when you're revising, kindly check, there's other examples. There's example 2 and 3 as well on the notes that I've uploaded on Moodle. You can look at them and see the different kinds of questions. Because of time, I just want us to cover all the 3 distributions. Then we can ask any questions you have along the way. Plus, after every distribution, there's different questions. So again, revision is highly recommended for us to understand the concept, and anyway they can ask a question. Okay, let's look at the Poisson distribution. Let's look at the Poisson distribution. Poisson distribution. So Poisson came from whoever invented this distribution. He's some French guy who was referred to as Simeon Poisson. That is where this funny term came from. So there's what is referred to as a Poisson distribution. So what kind of distribution is this? What kind of distribution is this? So the Poisson distribution, this distribution is used to model the number of events. It's used to model the number of events occurring within a given time interval. Within a given time interval. So for Poisson probability, our distribution, what you can also say is that this distribution, so we can say that the Poisson probabilities are highly useful when there is a large number of n independent trials, when there are a large number of n independent trials with small probabilities of success. With small probabilities of success occurring over a given period of time. Occurring over a period of time. So what's this kind of distribution does? It main point number one, it models the number of events that occur within a given time interval. The most common type of example that we use with the Poisson distribution is whereby consumers go to the bank. If you go to a particular bank, you always go for your ticket from the machine, get your ticket number, and it has like an average waiting time, which might or might not be correct. But the highlight or the important bit is that the event itself is a customer entering the bank and having to stay along the waiting line. Then the time interval is now the amount of time will be required to wait before you get served. So anything to do with customers in waiting lines is a good example of a Poisson distribution, whereby we are modeling the number of events, and these events are occurring within a given time interval. There's other different examples we've been given here for a Poisson distribution. So these are the examples we're talking about. Look at this, a fair coin is tossed 10 times. What is the probability that exactly 6 heads will occur? If 3% of electric bulbs manufactured by a company are defective, find the probability that in a sample of 100 bulbs, exactly 5 are defective, and so on and so forth. So these are all questions to do with the binomial distribution. So once you determine that it's either a success or a failure, automatically you rush to your PDF, not your PDF, your PMF for a binomial distribution. So back to Poisson. We have other examples here. Look at this. We are being told, for instance, the number of hits to your website in a day. So that means if maybe you're running a company, or maybe you're just a web developer and you want to monitor how many people visit your website in a day. For this particular instance, you need to model this using a Poisson distribution, because you are looking at the number of hits. So that is the number of events that will occur in a given interval. In this case, the interval is under a day. There's other examples there, the number of calls that arrive in each day on your mobile phone, the rate of job submissions in a busy computer center per minute, and so on and so forth. So anything to do with a number of events over a given time interval, we refer to this, or rather such instances can be modeled using a Poisson distribution. So with that understanding of the definition of the distribution itself, we can go to the formula. So since you're still dealing with a discrete distribution, the PMF for a Poisson distribution is given by the following. The probability of the random variable x will be equal to lambda. So lambda is just a Greek term. It's the same way I'd call something. I'd say 4x plus y is equals to 6. So instead of using these unknown variables, in statistics, we have Greek letters as well. So lambda is one of those Greek letters. So for this one, you can simply say we are talking about 4 lambda plus y is equals to 6. So it's just an unknown variable and it's referred to as lambda. So the formula will be as follows: lambda raised to the power of x multiplied by e. E is just a number. E is normally 9 point something, I'm not too sure. E is just a number. It's the same thing as saying pi. If we talk about pi, you're talking about 3.142. So E is also a given number. So E raised to the power of negative lambda, then divided by x factorial. For values of x from 0, 1, 2, all the way to n. So this is the PDF, or this is a formula for the Poisson distribution. So we can see the value of x can either be a 0, 1, 2, all the way to n. Then which other unknown variable do we have? We need to also determine the value for lambda. So when it comes to a Poisson distribution, lambda is what is referred to as the shape parameter. It shapes the distribution. And the shape parameter here basically indicates, so this indicates the average number of events. This indicates the average number of events in the given time interval. In the given time interval. This indicates the average number of events in the given time interval. So for instance, let's go back to the bank example. Let's say you want to monitor the number of consumers or customers. So the event is the number of customers in the waiting line occurring over a given time interval. Say you want to observe how many customers came in between 9 to 10 a.m. Have it as, say, 6 customers. Then from 9 to 10 a.m., how many customers came? There were about 17. From 10 to 11, and so on and so forth. So this value of 6 indicates the number of events, which is 6 people in the waiting line over a given period of 1 hour between 8 to 9. So in such an incident, your lambda here will be a value of 6. So what I'm just trying to say is lambda indicates the average number of events in the given time interval. So we'll see this as we do an example of how we can, of how we interpret this shape parameter. But it's basically the average number of events. So that's our formula for the Poisson distribution. Then you go to notation. So how do we represent a Poisson distribution? We say that random variable x follows a Poisson distribution. So this is PO. Random variable x follows a Poisson distribution. I don't want it to look like a subscript. It's only that the P is capital, then you have O. Poisson distribution with the parameter lambda, because this is the only unknown parameter that we need to find. The values of x will have it, of course. So this is represented as follows, or again, you can just write it in full and you read it as x follows a Poisson distribution with shape parameter lambda. With shape parameter lambda. Then when it comes to the mean and variance, for a Poisson distribution, the mean is equal to the variance, which is also equal to the shape parameter. So mu is equals to sigma squared, which is also equal to the shape parameter. So if we go back to the short example that I gave about the shape parameter being a value of 6, if the shape parameter is 6, then that means the mean of that distribution is also 6, and the variance of that distribution is also a value of 6. So if you're given a distribution and you've already identified it's a Poisson distribution and you're asked to compute the variance, yours is to simply identify the value of the shape parameter, then say by definition, the mean is equal to the variance and it's also equal to the shape parameter. So they're always similar like so. Very simple, that's all to do with that. So the names might sound, oh, what the hell are we talking about here? But it's just a statistical term, it's just a definition. But when it comes to understanding, it simply models the number of events occurring within a given time interval. So with that, we can look at an example for a Poisson distribution question. So we are told that consider a computer system. Consider a computer system with Poisson job arrival. So for this one, luckily, they've already told us it's a Poisson distribution, so we don't have to think much about it. So some of them, they'll be clarified. Some of them, you'll be given a scenario where, like I said earlier, you determine whether it's a binomial distribution, it's a Poisson, or it's a normal one. So we're told to consider a computer system with a Poisson job arrival stream, the Poisson job arrival stream at an average of 2 jobs per minute. Average of 2 jobs per minute. Determine the probability that in any 1 minute, in any 1 minute interval, there will be 1, 0 jobs, 2, exactly 3 jobs, 3, at most 3 arrivals, and 4, more than 3 arrivals. So we are told to consider a computer system with Poisson job arrival stream at an average of 2 jobs per minute. Okay, sorry about that. What was I saying? We are saying this is a computer system. It's a job arrival system that receives at least, not at least, it receives an average of 2 jobs per minute. So you want to determine the probability that in any 1 minute interval, there will be 1 0 job. So how do we go about it? For this particular one, we're told it's a Poisson distribution. So that means that our PDF is given by PMF. Our PMF or our formula for Poisson distribution is given by lambda raised to the power of x, then exponential raised to the power of negative lambda divided by x factorial. So that's our formula for the PMF. So the first one, we want to determine the probability that x will be equal to 0. So that means the probability that in under a minute or in a given minute, they won't receive any job. So that's why we are saying we want to compute the probability that x will be equal to 0. So this is equal to what? We need to find the value for lambda. We have the value for x. For this particular question, x is equals to 0. Then what about our value of lambda? We said lambda is the shape parameter that indicates the number of events over a given time period. So for this particular question, we are told that it normally receives an average of 2 jobs per minute. So that means lambda will be equal to a value of 2. So the number of events is 2 jobs, then the given time interval is per minute. So lambda will be equal to 2. So what is the probability that x will be equal to 0? So ours, we are left with substituting these values. So lambda is equals to 2. So we'll have 2 to the power of x, which is 0. So we'll have 2 to the power of 0 multiplied by e raised to the power of negative lambda. So e raised to the power of negative 2 divide by x factorial. So divide by 0 factorial. That will give you your probability. So 2 raised to the power of 0, of course, is 1. Then 1 multiplied by e raised to the power of negative 2. I hope you also know how to do that from our calculators. E raised to the power of negative 2. From here, I have 0.1353. Then divided by 0 factorial. 0 factorial is a value of 1 as well. So my probability here will be equal to 0.1353. So that's going to be the probability that x is equal to 0. What about the probability that it will receive exactly 3 jobs? That means you want to compute the probability that x will be equal to 3. So same formula, lambda is still a value of 2. So the shape parameter doesn't change. Raised to power x this time is a value of 3, multiplied by e raised to the power of negative 2, then divide by x factorial, divide by 3 factorial. This will give you the value for the probability that x is equals to 3. So for this one, I'll have multiply this real quick from your calculator. We have 8 multiplied by e to the power of negative 2 divided by 3 factorial. This gives me 0.1804. So that's the probability that x will be equal to 3. Then number 3, what is the probability that it will receive, or what is the probability that in 1 minute interval, there will be at most 3 arrivals? At most 3 arrivals. So this means the maximum you can receive is 3 arrivals. Again, this is a discrete distribution. So this is equivalent to what? To x being either less than or equal to a value of 3. So by at most, it means that there can be either 0 jobs in under that minute, there can be 1 job, there can be 2 jobs, or there can be a maximum of 3 jobs. So with that, this caters for x from x being a value of less than or equal to 3. So we said if you have such an interval, this is equivalent to getting the probability of x is equals to 0 plus the probability of x is equals to 1 plus the probability of x is equals to 2 plus the probability of x is equals to 3. So we have our value for x is equals to 0. We need to get the value when x is equals to 1, 2, as well as 3. So this is equals to what? Look at this, 2 to power 0 multiplied by e raised to power negative 2 over 0 factorial plus x is equals to 1. We'll have lambda is still a value of 2. 2 raised to the power of x is 1, multiplied by e raised to the power of lambda, which is still negative 2, divided by 1 factorial. Then plus, when x is equals to 2, we'll have 2 raised to the power of 2, multiplied by e raised to the power of negative 2, divided by 2 factorial, then plus, when x is equals to 3, lambda is still 2, 2 to the power of 3, multiplied by e raised to the power of negative 2, divided by 3 factorial. So you can easily just get these values from the calculator. Alternatively, we can remove this common factor. There's a common factor here of e to the power of negative 2. So if we remove that outside, what are we left with? For the first one, 2 raised to power 0 is 1. 1 divided by 0 factorial is 1. Plus 2 to power 1 is 2. 1 factorial is 1. 2 divided by 1 is equals to 2. Plus 2 raised to power 2 is equals to 4. And 2 factorial is a value of 2. So 4 divided by 2 gives you 2. Then finally, plus 2 raised to power 3 is 8. And 3 factorial is 6. So we have 8 over 6. So this will give you the solution there. So you have 1 plus 2 plus 2 plus 8 over 6 multiplied by e raised to the power of negative 2. So this will give me 0.8571. I hope the silence means that this is cheap mathematics and that you're understanding. Collins, Lagarde, are you understanding? Collins, Lagarde. Collins is nowhere to be seen.
I am there, madam.
Okay. Then the last bit, we want to guess the probability that, determine the probability that in any 1 minute, we'll have more than 3 job arrivals. So what does more than 3 job arrivals mean? It means we want to get x is greater than 3. This means we want to get x is greater than 3 job arrivals. So how do we get this? Since we don't have the upper bound, because for this one you're talking about, it can be anything. You can have 0 jobs at under a given 1 minute interval. You can have 10 jobs, you can have 2 jobs, and so on and so forth. So since we don't have the upper bound, the only way we can get this probability is by taking 1 minus the probability of x being less than or equal to 3. So this is going to be 1 minus, if you look at this, the probability that x is less than or equal to 3 is the same thing we are from computing here. So we'll have 1 minus 0.8571. 1 minus 0.8571 is equals to 0.1429. So that's just an example of how we compute a Poisson distribution. So the important thing for this is to understand what you mean by the shape parameter. That is the only unknown variable that you might need to find. The values of X, you can easily just deduce them from the question. So maybe you can look at one last example for a Poisson one. Let's look at another. We are told that if there are 500 customers, per 8-hour day in a checkout lane, what is the probability? What is the probability that there will be exactly 3 in line during any 5-minute period? So we are told that if there are 500 customers per 8-hour day in a checkout lane. So out of an 8-hour day, there's normally 500 customers. Then we are asked, what is the probability that there will be exactly 3 in line during any 5-minute period? What is the probability that there will be exactly 3 customers in line during any 5-minute period? So like I said, you see for this question, they haven't really told us it's a Poisson distribution. So you go eliminating, determine, is this a binomial distribution? Of course it's not. There's nothing to do with 2 possible outcomes here. Is this a Poisson distribution? It is, because you're talking about a given event, which is customers at a checkout lane over a given time interval, which you're told that they're normally per 8-hour day, they're normally 500 customers. So once we've determined this follows a Poisson distribution, we can have our formula. So the probability for any random variable X will be equal to lambda raised to the power of X multiplied by E raised to the power of negative lambda divided by X factorial. So with that, we need to get the shape parameter. What is the question asking us for? The probability that there will be exactly 3 customers in line during any 5-minute period. So we are computing the probability that X will be equal to 3 customers. We want to know the probability that X is equals to 3 customers during any 5-minute period. So we have our value of X, which is 3. We also need to get our value of the shape parameter. So how do we get the value of lambda? So look at this. We are saying that if we have 500 customers per 8-hour in a day, so we can convert this to minutes because we're talking about a 5-minute period here. So if there are 500 customers, an average of 500 customers under a period of 8 hours. 8 hours is equivalent to how many minutes? 8 times 60, which is equals to 480 minutes. So remember what the shape parameter means. Lambda means that we want the number of events in a given time interval. The number of events in a given time interval. So if we have 500 customers in under 480 minutes, how many customers will you have in line for under a period of 5 minutes? because that is what you're interested in. So for 500 customers, we have in under 480 minutes, we'll have 500 customers. So how many customers would we expect? How many customers would we expect in under 5 minutes? So to get this, we simply cross multiply. So that means we'll have 5 divided by 480 multiplied by 500. So by 1 by 596, I want to leave it in a fraction form so that you don't round off so much, because 500 divided by 96 does not give you a whole number. It gives you a recurring decimal. So let's leave it as 500 over 96. So we talked about this being the expected value. Remember the expected value, when you talk about an expected value for a random variable, this is the same thing as the mean. Because listen to the question you asked. You wanted to determine the number of customers we'd expect in 5 minutes. So we can say that 500 over 96 is the expectation, which is denoted by mu. And again, by definition, we say that the mean is always equal to the variance, and which is always equal to the shape parameter. So if the value of mu is 500 over 96, then the value of lambda will also be equal to 500 over 96. So with that, you can go back to our formula. We'll have this is equal to lambda is 500 over 96 raised to the power of x. So x is a value of 3. Then multiplied by e raised to the power of negative lambda. So e raised to the power of negative 500 over 96. Then divided by x factorial, divided by 3 factorial. So that will give you the probability that there will be exactly 3 customers in line during any 5-minute period. So this will give me a value of 0.1288. And that will give me 0.1288. So that's another way in which we tackle Poisson kind of distribution questions. So again, you look at example 3. There's an example 3 there as well. You can tackle it. Also check online. Don't be so limited when it comes to examples. You can just do a quick Google search. You can just type out sample questions for Poisson distribution, sample questions for binomial, because at least for online questions, you'll have the working out as well as the solution. So this is another example which you can look at once you get to this point. Then there's a short exercise there that deals with Poisson distributions. Some of them have solutions, so you can pick one that has a solution and see if you'll get the same answer. Yeah. So the next distribution is a normal one. I want us to stretch a little. Take some water. Please make sure you come back in exactly what? Let's just take 10 minutes. Because the normal distribution is very important. Because for the normal distributions, you're going to be using tables, and I'd like us to understand how we read these tables. Otherwise, if I lose you from the beginning, for normal distribution, you can't really move. So it's 3:25. Let's meet at exactly 3:35. We look at the normal distribution, then call it a day.
Halo, halo, halo. Buka aja. Kasih baru di sana.
Okay, I think we can continue. I want us to look at the continuous distributions, and you said the only continuous distribution that you want to focus on is the most widely used distribution, which is what is referred to as a normal distribution. So even as the name suggests, we've been talking about binomial, Bernoulli, and many other statistical terms and terms for mathematicians and all that. But when it comes to this particular distribution, it's as normal as it gets. So what do we mean by a normal distribution? Say you have a given plot as follows. Let's say you have a given plot as follows. What example can I use? Let's say I'm going to the market. I'm going to buy some fruits. I want to buy a watermelon. So as an individual or the Kenyan that I am, mine would probably be, I want to pick out the biggest watermelon out of everything that's available in the market. So with all these melons, they come in different sizes. There's one that are bigger than the other. We have that those ones that are a little bit smaller, and so on and so forth. Now, as much as they're not of all the same sizes, there is a given mean value that you can associate with these melons. This goes back to descriptive statistics. We said one of the most used measures or one of the most used concepts to describe a given set of observations is the mean value. So as much as all these melons have different sizes, we have that given mean value such that if I was to plot the different sizes for these melons, I'd end up with such a curve. So this denotes my mean value. So this is mu, which is the mean. Then we have different sizes now for the observations. We'll have some that are smaller. You have some that are smaller, and you have some that are bigger than the rest. Then it ends up looking like so. So I'm trying to plot the graph for a normal distribution. It will look something like this. It will look something like this. So if this is the mean value, every observation along this curve is now all the other respective x observations. So this is x1, this is x2, this is x3, this is x4, and so on and so forth. So if you plot a given normal distribution, we end up with such a curve. So we have the mean at this point. The main property we have of a normal distribution is that it is bell-shaped. It has the shape of a bell. So a bell normally looks like this. It's bell-shaped and it's also symmetric. We talked about some of this concept when we were looking at measures of skewness. So by symmetric means, if I have point A towards the left corner, and I have point B towards the right corner, and I decide to fold this so that point B meets point A at this other side, I'll end up with exactly 2 halves. So for a normal distribution, the mean, like so, normally separates the given plot into 2 equal halves. So number one, we have that property where a normal distribution is normally bell-shaped, then which is also symmetric. Then another property we have is that the normal distribution is normally asymptotic. What does asymptotic mean? Asymptotic in this case means, look at the tails of my curve. So I have my x-axis as shown here. Then my observations, they tend towards the x-axis, but they never touch the x-axis. So these values become smaller and smaller as they tend towards infinity. They become smaller and smaller as they tend towards infinity, but don't touch the x-axis. So this is what is referred to as the asymptotic property, whereby towards the extremes, the observations tend to 0 as you proceed towards infinity. Then another property we have is for the mean. So we've said that for our normal distribution, the topmost bit represents the mean. And for a normal distribution, the mean is always equal to the mode, which is always equal to the median. So if the mean for these watermelons was say, the mean size for the watermelons is a value of 20, then that means the mode will also be 20 and the median will also be 20. So we have that property. Then we have the property that deals with the standard deviation. So the mean as well as the standard deviation normally determine the size or the structure of a normal distribution. For instance, if the mean value is a little bit lower, let's say the mean value is 10 instead, you might end up with such a chart. So instead of it looking like so, you'll have a lower peak as follows to indicate a lower mean. And you end up with such a distribution. Again, I said this has to be symmetric, so I might not hit it entirely, but anytime we draw a normal distribution curve, just remember that it has to be symmetric. This side should be equal to this side. So you see, if the mean is lower, then it changes or it dictates the shape of the distribution curve. So that's how the mean normally affects the curve. Then when it comes to the standard deviation now determines the width of the curve. If you look at these two curves that we have here, look at this black one, the one you had initially. The deviations from the mean represents the distance from these observations along the curve all the way to the mean. So if you look at these deviations, the deviations for the black ones are a little bit wider compared to the deviations we have for this red curve. So these are what you're referring to as the deviations from the mean. We said standard deviation is denoted as follows, as sigma. So standard deviation will denote that, or rather will dictate the width of the curve. So if you have lower deviations or smaller deviations, then the curve is not as wide. If the deviations are so large, like what you're seeing for the black curve, then we end up with a wider curve as follows. So we can say that both the mean as well as the standard deviation normally affect or dictate the shape of our normal distribution. Then another property that we have is that when you are talking, let me just take you back to discrete random variables first. When you're talking about discrete variables, we were able to compute probabilities at a particular point, whereby we were able to compute the probability of x being equal to 3, of x being less than or equal to 2, and so on and so forth. And you are able to do this using the use of different formulas for our discrete distribution, using the different PMFs. When it comes to a continuous distribution, we say the continuous distribution deals with a given interval or a given range of values. So since you're dealing with an interval, it's not easy to get the probability at a point. So what we do is we normally use this curve that we have here. We use this curve to estimate or to compute these probabilities. So the probabilities for a normal random variable is normally given by the area under this curve. So this entire total area normally represents the different probabilities for a normal random variable. So this is what is our focus of the normal distribution. We want to understand how we compute probabilities under the curve. So the entire curve gives the area. The entire curve gives the probabilities for a normal random variable, and the total number of probabilities within the curve again is a value of 1. So our property still holds here, that the summation of our probabilities is still equal to a value of 1. So the area under this curve represents a value of 1. We'll look at how we compute these values in a second. So that's another property, that the area under the curve represents the different probabilities for different normal random variables. And that the probabilities under the area under the curve, that is always equal to 1. Then the last the last empirical rule that we have, the last property I want to talk about, I think I'll have to do away with this. The last property that we have is that we refer to this as the empirical rule of normal distribution, empirical rule. So we're saying again, you have the same normal distribution, it's symmetric. So if my mean is at this point, this topic is really challenging my graphic skills. I think that's why some of us are mathematicians rather than graphic artists. I think that's a career that I'll flop at. Anyway, I'm just trying to make it as symmetric as possible. So we have such a normal distribution. The empirical rule states that when you're computing when you're computing your different probabilities, this is my value of mu. And you said we can get the different deviations from the mean. For instance, let's say we have a point at the left-hand side and you have another point at the right-hand side. So these points represent plus or minus 1 deviation from the mean. So I can call this mu minus 1 deviation, and this is mu plus 1 deviation. So at this point, from mu minus 1 deviation all the way to mu plus 1 deviation, we can say that 68% of all our probabilities fall within this particular range. Like I've said, this is an empirical rule. There's nothing we can do about it. By definition, the deviation by plus or minus 1 deviation from the mean gives us such a plot. So 68% of the values of a given normal random variable will fall under this particular section. Then we can also talk about 2 deviations from the mean. So we'll have mu minus 2 deviations and mu plus 2 deviations. So we'll have our other points at this section here, have another point here. So for this particular range, we say that 95% of the values for a normal random variable fall under this particular area. So this entire area of the curve, from here, if I was to shade it out all the way to this other edge of it. Then finally, the third deviation, we say 99% of our values or of our random variables will fall within 3 deviations from the mean. So we'll have mu minus 3 deviations and we'll have mu plus 3 deviations. So this area under the curve, from this point all the way to this point, represents 99% of values of a normal random variable. So again, this is what we refer to as the empirical rule of probability. So those are some of the properties you need to understand about a normal probability distribution before we continue on the computations and whatnot. So I hope you're together up to that point. All of that was just defining what a normal distribution is, so you're able to understand what you're talking about. So we are saying it's a normal distribution because so many different natural phenomena normally end up with this. The example you use is for a melon. Let's talk about the height of students in this class. I know there's some of us who are taller than the rest. I know there's some who are shorter. Of course, there's that one student who's ordinarily short, or there's one guy who's weirdly 6.4 feet and so on and so forth. So besides the fact that there's this very low or very high observations, we'll find that most of us will fall within a certain mean. So if you decide to plot these observations, you still end up with such a distribution. Even when you talk about, another good example we use is the IQ, the different levels of IQ. There's those guys who are really smart, and there's those guys who are really struggling to understand what the hell a normal distribution is. But most of us will fall around the mean, whereby our IQ is not so low, our IQ is not so high, but it is just within the given average. So most of the natural phenomena, normally, if you decide to plot the observations, you end up with what we refer to as the normal distribution. So that's what we mean by definition. With that, you can now look at its formula. So a formula for the normal distribution is given as follows. So since this is a continuous random variable, we talk about a what? We talk about a PDF. Remember, for continuous ones, we talk about PDF. For discrete ones, we talk about PMF. So let's talk about the PDF of a normal distribution. The PDF of a normal distribution is given by the following formula. So the function of this PDF, so it has the parameters mu as well as the variance. So mu is for the mean, sigma squared is the variance. So these are the parameters in question, and the formula is given as follows. We have 1 divided by the square root of 2 pi multiplied by the variance, then this multiplied by e raised to the power of negative x minus mu squared divided by 2 multiplied by sigma squared. So this is the formula we use for the normal distribution. So this is for exponential. So this can still be rewritten as 1 over the square root of 2 pi sigma squared, exponential of what? Exponential of negative x minus mu raised to the power of 2 divided by 2 multiplied by the variance. So this and this are one and the same thing. So this is what we refer to as the PDF of a of a normal probability distribution. So the PDF is given by this formula. So the notation, of course, will be as follows. We say that X follows a normal distribution. So normal is denoted by capital N with a mean of mu and a variance of sigma squared. So this is how we denote the normal distribution. So since it's a normal distribution, mean is the same value we've been talking about. If you need to compute summation of fx divided by n or summation of x divided by n for the normal data sets we've been looking at, because this is for a normal distribution. Same thing with the variance. Variance, we also use the formulas we were using before. So this is the notation for that. With this, you can now go into how we compute the probabilities for a normal distribution. So how do we compute these probabilities? I think we can all agree just by looking at this formula. I'm sure some of us are just getting tired of how long this or how lengthy this formula looks. It looks a little bit tedious for us to work with. So what happens with the normal probability distribution is that instead of working with this PDF, we normally standardize it first. We standardize the X variable. Again, we have mu. Mu is our parameter. We have sigma squared, which is the variance, which is another parameter. So look at this. 2 is a known value. Pi is a known value. Sigma squared is a parameter which you can obtain. And mu is also a parameter which you can easily obtain. What about X? X is the random variable in question. So what we do is that instead of dealing with this entire formula, we standardize the random variable X. We standardize the random variable X. How do we do this? How do we standardize this random variable? We can say that standardization So this standardization is accomplished using the formula for the Z-score. Using the formula for a Z-score. And this formula for the Z-score is given by Z is equals to X minus mu divided by sigma. And this follows a normal distribution with a mean of 0 and a variance of 1. So standardizing basically means that I assume that, not assuming, we standardize. Instead of using any other value for the mean and the variance, we standardize it to the mean being equal to 0 and the variance being equal to 1. So standardization will give us this particular Z-score. So what this Z-score does is what we use to compute the same probabilities I've spoken about when you talked about the area under the curve. So you'll have your normal distribution curve like so. So these Z-scores are what we're going to use to compute the probabilities under the curve. And we normally calculate, or rather we get these Z-scores from the standard normal distribution table. That's what I talked about. So we'll be getting these values from standard normal distribution tables. I'll show you how that looks like. So the tables are used to obtain the probabilities. And this is our formula for the standardization. So once you get your Z-score, then you can just go back to the tables for you to compute the corresponding probabilities. So if you look at this formula, we'll see how to compute this Z value. X, we've said, is the random variable in question. Mu is the mean, and sigma is the standard deviation. So note, for this one, you're talking about SD, not the variance. This is divided by SD. So if I cross multiply this, I'll have Z multiplied by the standard deviation is equals to X minus mu. And the value of X would be equal to Z sigma plus mu. So sometimes you have the value for the Z-score, you have the mean, you have the standard deviation, but you don't have the value of X. So you can still get the random variable using this formula. So you can work backwards to get the value of X, or you can just operate normally by computing the value of the Z-score using this particular formula. That is X minus mu divided by sigma. So anytime you're given, what I'm saying in many words, anytime you're given any distribution or any function, that is any PDF that constitutes a normal distribution, what you're going to be doing is we first standardize it. So by standardizing, let's say we're talking about computing the probability of, let's say we want to compute the probability of X being less than or equal to a certain probability or a certain value here. So what you're going to do, we're going to standardize this value of X. And once we standardize it, we end up with a Z-score. So now we'll be talking about the probability of Z being less than or equal to Z. Because the tables you're going to be looking at, they give us the Z-scores. Let me just show you this table. This is the table you're going to be using. Probability distribution. Standard normal. Okay, here it is. So these are the tables. I think some of us have encountered it before. Most of the time we have it in our SMPs, though for our course, we don't really need the SMPs. So this is what I'm referring to as the standard normal distribution table. So we're being told that this table values represents the area to the left of the Z-score. See how they have highlighted that we're talking about the left? What does this mean? Table values represent the area to the left of the Z-score. This means that if I go back to my curve, if this is my normal distribution, and this is my Z score. So I'll have a normal distribution like that. And say Z is at this point. This is what you're referring to as the Z score. So if Z is at this point, this is marked all the way to where the curve is touching it. So that table that I've just displayed gives us the probability to the left of the Z score. So it gives us this area to the left. Because sometimes you're asked to calculate this area to the right, yet the table gives us the area to the left. How do we go about it? That's what we want to see. Then once you're able to get the Z score, all these values inside are the respective probabilities. So we have the Z score at the top here, at this particular row, and this particular first column, from negative 3.9 all the way to the positive values. Then all these values in the middle, all these other values are now the respective probabilities. And this is what we use to compute the probability for a normal distribution. I hope you're together. So let's look at how we compute these probabilities using these tables. Let's look at how we compute these probabilities. So there's different rules that we use. There's different rules that you need to adhere to when reading these particular probabilities. We have 4 rules that I want us to look at. We normally apply them, we interchange them once in a while when you want to compute a probability. So rule number 1, first of all, we've said that the Z score, it gives us the table gives us the Z score rather than the X variable. So we have to standardize the X variable first. So for rule number 1, I have that normal distribution as follows. Rule number 1 states that if I want to get the probability that a given Z score is less than or equal to a given value of A, you simply just read the value that is on the table. So this notation, this is again, this is another Greek letter. This is referred to as capital phi. It's just a Greek letter. So we'll be using this phi to represent the Z score. So for us to get the probability of Z being less than or equal to A, we just read the Z score directly from the table. So normally what happens, let me go back to the plot so you can see what I mean. So let's say I have a point A. This is the same point I'm speaking of at this point. So I have point A over there. So point A, if I join it to my curve, it will look like so. And you're saying that generally the tables for the standard normal distribution, we've already said they give us the left score. They give us the left-hand side of the Z score. And this table normally reports, I think this is also important to mention, that the table normally reports, it reports the cumulative normal probabilities, the cumulative normal probabilities for the value P is less than the probability that Z is less than or equal to a given value. So this is the standard value that it shows you. And when it comes to representing it on a particular graph as shown, the default value that the table gives us, we are saying is to the left-hand side of the Z score. So this A is equivalent to the Z score that I'm talking about. I do want to use a small z here so that we don't confuse ourselves. This can be any letter here. You can still talk of a small z, but I think we can say let A represent the Z score so that you don't confuse these two Z's. So by default, if I want to read or to get the probability that Z is less than or equal to A, I simply read this value that I'll find here. It will give me the value to the left. Then in case it's a negative, that is the probability that Z is less than or equal to negative A. What we do is simply take 1 minus what we had for the positive value. So we'll have 1 minus the Z score for A. So of course, let's do this with an example so you can understand what I'm trying to say. Let's say you want to compute the probability. Let's say you want to compute what? You've been told to find the probability that Z is less than or equal to a small z here. I don't know if I use Z or A. Let me use A for uniformity and to avoid confusion. Let's say compute the probability that Z is less than or equal to A. For A is equals to 1.65 and A is equals to negative 1.65. So how do we compute these probabilities? So this question you're being asked to compute the probability that Z is less than or equal to 1.65. Compute the probability that Z is less than or equal to 1.65. So how do we go about it? We said by definition, the table normally reports this probability. It normally reports the probability that Z is less than or equal to A. Let's use A for uniformity. It reports the probability that Z is less than or equal to A. So if you're told to compute this probability, what you do is you come back to, you have to have a sketch. So we can sketch this normal curve. So we have that value. Let's say we have 0.0 somewhere there. So you have your symmetric normal curve. So you have 0, 1, and 2. And you also have 0, -1, and -2. And you want to compute the probability that Z is less than or equal to 1.65. So where is 1.65? Somewhere here. 1.65 is somewhere here. And you want to compute the probability that Z is less than or equal to 1.65. So that means you're interested in the left side bit. The left side, because this is where we have less than or equal to. So you want to compute the probability of this side of the area under the curve. So this is 1.65. So you want to compute Z is less than or equal to 1.65. And we said by definition, the table will always give you the side to the left of the Z score. So since we are being asked indeed for the left side, all we need to do is read the probability for the Z score of 1.65. So we come back to the table. And look for 1.65. So again, it starts from the negatives. The table normally reads to 2 decimal places. So this first value here is negative 3.90. Then this second one is negative 3.91. Next one, negative 3.92, and so on and so forth. Look at this one that I've highlighted. So this, the one that I've highlighted is equal to negative 3.53. I hope you can see how we read it. What about this one towards the end over here at this point? So this is equal to negative 3.29. So we want to read the Z score, the probability for the Z score 1.65. So we scroll down to 1.65. 1.6 is somewhere here. So 1.6, we have it there towards the bottom. Then we move across the table up to 1.65, which will give us this value that you can see there. So I'll share the table so that you use one standard table. Alternatively, if you have an SMP, the same values should be there. If you don't, just do a quick Google search and write the standard normal distribution table. You should be able to get such a table. So we have it there. Our value for 1.65 is equals to 0.9505. 0.95053. 0.95053. So this would be equal to 0.95053. And then by this rule number 1, what about the negative of it? So the negative will have, if you want to get the probability that Z is less than or equal to negative 1.65, you simply take 1 minus what you've gotten here, 1 minus 0.95053. So what does that give you? 1 minus 0.95053. This gives me 0.04947. So that's going to be the probability that Z is less than or equal to negative 0.15. Alternatively, instead of using this rule, remember we've said the tables also give us the values for the negatives. So we can also read directly. Let's read directly from the table and see what we'll get. We want to read now negative 1.65. So I'll go back to the table. I'm looking for negative 1.6. So negative 1.6 is somewhere there. I want negative 1.65. So this is 0, 1, 2, 3, 4, 5. So negative 1.6 is here. Then negative 1.65 would be 0, 1, 2, 3, 4, 5. We have it as this value. We have 0.04947. 0.04947. And if you go back to what we have here, we end up with the same value, which is 0.04947. So you can either just get it directly from the negative side of it, or you can use this rule. Why I'm looking at both sides is sometimes the table, you can just be given the positives. So if you're given only the positives, then you need to remember this. But if the table has the negatives, yours is to just read it directly, and we end up with the same value. So that is rule number 1. What about rule number 2? So rule number 2 states the following. We can also get the probability that Z is greater than A. Probability that Z is greater than A. We'll first represent this in form of the normal distribution curve, so we can see what we're interested in. We're talking about, so we have a normal curve there. You want the probability that Z is greater than A. So if my A is at this point, so say my A is at that point, the probability of Z being greater than A means now we are looking at the right-hand side. Greater than means we look at the right side, less than we look at the left side. So this probability means that you want to compute the probability that Z is greater than the Z score A. So the side you are going to be interested in is the side that I've shaded. So when it comes to reading the graph, again, don't forget, not the graph, the tables. The tables give us the values for the left side of the score. So the table will give us the red bits. But for this particular question, we want the shaded black area. So how do we get this shaded black area? This is going to be equal to whatever we get here, we take 1 minus the Z score of A. Because the value that you'll get is for the left side, but you're interested in the right side. And we know that the total cumulative area for this curve is a value of 1. So for us to get the black side, we take 1 minus the Z score of A. Then again, if we talk about the negative, for negative, we said once you have the positive one, you just subtract. So for you to guess the probability that Z is greater than or equal to A, this will now be equal to 1 minus whatever you have here. So 1 minus z score of A. Or alternatively, you read it directly from the table. If you read it directly from the table, what does that mean? We'll see how we go about it. So let's look at an example. Let's look at an example for that kind of scenario. So we are told to compute the probability that so you want to compute this probability. Compute the probability that Z is greater than A, for A being equal to 1.02. A is equals to 1.02. Let's take a 1.5 so that you do for both, where A is equals to 1.5 or A is equals to negative 1.5. So we can see for both sides. So how do you go about it? Let's look for the probability that Z is greater than 1.5. So how do we go about this? First things first, always have a sketch of this table, of the normal distribution curve. I can tell you for free that it will guide you on what exactly you're supposed to do. So if this is my point 0, this is my point 1, and this is my point 2, and I have -1 and -2. I want to get the probability that Z is greater than 1.5. So 1.5 is somewhere here. And I want to compute the probability that Z is greater than this. So which side do I want? I want this shaded area. So how do I get this shaded area? I first read the Z score for 1.5, which will give me the left side bits. So if I read the value for Z at 1.5, it will give me the left side bits, but I'm interested in the right side. So I'll take 1 minus whatever I read here. So this is equal to what? 1 minus Z score at 1.5. We'll go back to our table, come to 1.5, come to 1.5. We have it as 0.93319. 0.93319, 933.19. So I'll have 1 minus 0.933 something. I knew I'd forget. 0.93319. 319. So subtract that to give you that probability. So you'll have 1 minus 0.93319, which gives you 0.06681. So that will be the probability that Z is greater than 1.5. What about the probability that Z is greater than -1.5? So again, have your sketch, have your cumulative curve as follows. So this is 0, this is 1, this is 2, -1, -2. So you want the probability that Z is greater than -1.5. So -1.5 is somewhere here. And since it's greater than, we are interested in this side, in the right-hand side of the shaded bits. So that means we get for the left, then whatever value we get here, we'll take 1 minus that value. So we'll read the Z score for point -1.5. Z score for probability for the Z score -1.5. We go back to -1.5, which is 0.06681. 0.6681, 0.06681, 0.06681. So this is for the left side bit, but remember we are interested in this other side. So we'll do 1 minus 0.06681. That should give you the probability. 1 minus 0.06681. So I have here 0.93319. So that's going to be my probability that Z is greater than negative 1.5. So the more probabilities you read, the more you'll grasp it. But for sure, if you have the plot for the normal distribution and you understand that the values from the table will give you your value towards the left score. So yours is to determine what the question is asking. Do I want the left side or do I want the right side? If you want the left side, you take the value as it is. If you want the right side of it, then you have to take 1 minus whatever value you have. And you'll end up with such a probability. I hope you're together up to that point. So that's rule number 2. Then you have rule number 3. You have rule number 3 that states as follows. So you have to know how to read these probabilities before we compute any questions, any problems related to normal distributions. So rule number 3 states as follows. The probability of A, the probability that Z falls within this given interval from A all the way to B is equal to the Z score at B minus the Z score at A. The difference, that is probability for the Z score at B minus probability for the Z score at A. So in terms of the plot, this is how it looks like. So if you have your normal distribution like that, you have your curve as follows. So you can have point A at this point, then you have point B. So for you to get the probability from A all the way to B, you want to get the probability of this shaded area. And since you're saying that the standard normal table gives us the values to the left of the Z score, if I get the Z score at B, it will give me the entire area up to the end here. Then minus, if I take now the Z scores for A, it will give me the side to the left all the way to the end. Then I'm left with this difference in the middle. Hence why we are saying, if you want to get the probability for a given interval, you simply compute the probability for Z score B minus probability for Z score A. An example, e.g., let's say A is a value of what? Let's say A is a value of -1 and B is a value of 1.8. I don't want to use 1.5, we've done that. We have from A is -1 and B is 1.8. So that means you want to compute the probability from -1 all the way to 1.8. So for you to get this probability, you get the Z score for point B, which is 1.8, minus the Z score for point A, which is -1. So we'll go to our table, read the value for 1.8. So go back to our table, read the value for 1.8. What do you have for 1.8? 1.8, you have 0.96407, 96407. 0.96407. So we have 0.96407 minus the Z score for -1. So we'll go back to our value, our table rather. Let's look for the Z score for -1. -1 is equivalent to -1.0. So the Z score here is 0.15866. 0.15866. So minus 0.15866. So that will give you the probability for that particular interval. So 0.96407 minus 0.15866. This gives me 0.80541. So that will be the probability for that particular interval. Then you have the last rule, which is rule number 4. Rule number 4 is still to do with intervals, but now we want where we're dealing with from negative A all the way to positive A. So we have a common constant here, only that you are going from negative A all the way to A. So that can be from negative 3 all the way to 3, can be negative negative 5 all the way to positive 5, and so on and so forth. So the probability from negative A all the way to A is given by this formula. So this would be equal to twice the z-score for A minus 1. Twice the z-score of A minus 1. Where am I deriving this formula? We can see where it comes from. Using this rule number 3, the probability from negative A all the way to the interval, all the way to the upper limit of A is the same as, according to rule 3, the z-score of A minus the z-score of negative A. Then still by definition, you are able to see that the z-score of negative A is equals to 1 minus the z-score for positive A. That's what we've been saying all along. So this is equals to the z-score of A minus 1 minus the z-score of A. So if you open up these brackets, you'll end up with z-score A minus 1 plus z-score A. So you'll end up with twice the z-score of A minus 1. So this is just the derivation, but the formula is as follows. So if you have an interval with a similar constant, 1 from the negative all the way to the positive side of it, yours is to get twice the given z-score, then minus 1. Example, let's say A is a value of 2.58. Let's say A is a value of 2.58, and you're asked to compute that probability. So you want to compute the probability that you'll go from negative 2.58 all the way to positive 2.58. And by rule number 4, this is equals to twice the z-score of 2.58 minus 1. So we need to compute the z-score for 2.58. So again, go back to our table. Let's go to point 2.58. So 2.5 is somewhere here. Then 0.8, this is 0.0, 1, 2, 3, 4, 5, 6, 7, 8. So 0.8 is somewhere here. So we have it as 0.99506. 0.99506. So we'll have 2 into 0.99506 minus 1. That will give you that probability for that interval. So we'll have 2 multiplied by 0.99506, then minus 1 to give you 0.99012. So that will be your probability from negative 2.58 all the way to 2.58. So even if you're given a different value, you still use the same principle. If it were negative 4.1 all the way to positive 4.1, you still get the z-score of 4.1, multiply it by 2, then subtract 1 to give you your probability. So those 4 rules, kindly I urge you, go back and look at them again, because you'll have to be using them time and again as you answer any questions that do with normal distributions. So with those rules, you can look at an example of now how an exam scenario can be, or how a question can be asked. All we've been doing is how to compute probabilities for a normal distribution. So let's look at a simple example. I hope we have this. Can I do away with it? Anyone who's still using this page? Okay. Look at this example. We are told that a random variable x, follows a normal distribution with a mean of 50 and a variance of 25. Remember the notation. So if you see something like this, it means random variable x follows a normal distribution with a mean of 50 and a variance of 25. Then you're asked to compute the probability that a random variable x lies between 45 all the way to 60. Find the probability that a random variable x lies from 45 all the way to a value of 60. So how do we go about this? Step number one, we said when you have a problem to do with the normal distribution, the first step is always to standardize. And standardizing means that you assume that this particular distribution now has a mean of 0 and a variance of 1. So what was the formula we used for standardization? We said standardization is denoted by a z-score. Standardization is denoted by a z-score. Z-score equal to what? Z is equals to x minus mu divided by the standard deviation. X minus mu divided by the standard deviation. So to standardize this x variable, this is how we go about it. We'll have the interval looking as follows. So we want to transform this variable to a z-score. We want to transform this from variable x to z-score z. So how do we do this? We'll have it as, so this is equals to the probability. So take your lower interval or your lower bound, which is 45, and standardize this. So we standardize using this formula. So take your value of x, which is 45. Then 45 minus the value of the mean. The mean we've been given as a value of 50. So 45 minus 50 divided by the standard deviation. So if the variance is 25, then the standard deviation is the square root of 25, which is a value of 5. Then we'll have, that is the lower limit. So we have that is less than or equal to z. So we've standardized it. So we are no longer talking about random variable x, but we're talking about the value z, the z-score that is. Then for the upper limit, same thing for standardization. Take your value of x minus mu. X minus mu is 60 minus 50. Divide by the standard deviation, which is 5. So this would be p into what? 45 minus 50 divide by 5 is equals to -1, is less than or equal to z, which is less than or equal to 60 minus 50 is 10. 10 divided by 5 is equals to 2. So what you're generally being asked is to compute now this particular probability that the z-score lies from -1 all the way to 2. So if you're to represent this in the normal distribution curve, we're talking about point. If this is my 0, I have point 1, 2. I have point -1, point -2. So we want from -1 all the way to +2. We want this area in the middle. And we said to get the area in the middle, if you have different variables, this is equivalent to rule number 4, where we talked about what? Rule number 4, we talked about if you have the probability 3, if you have the probability of A less than or equal to that all the way to B, for me to get this probability, it's going to be equal to the probability of the z-score at B minus probability at A. So for this one, we'll have, this would be equal to our z-score at point B, which is 0.2, minus the z-score at point -1. So we'll go back to our tables. We find the z-score for 0.2. So come back to our table. What's our z-score for 0.2? 2.0 is equals to 0.97725. 0.97725. So we'll have 0.97725 minus the z-score at -1. So again, come back to our table. You want the z-score for -1. So I'll come back to -1. -1 is here. We have 0.15866. 15866. So this difference will give us whatever they're asking for. So 0.97725 minus 0.15866 to give me 0.81859. So that will be the probability in question. So this is why we had to do all those rules before we come to the computation, so that when you reach this point, we know which rule to apply so that you get the probability. What about, let's have another example. Let's have another example. Another example, you're told that suppose X follows a normal distribution with a mean of 30 and a variance of 16. Find the probability that X is less than 40. Find the probability that X is less than 40. How do you go about that? First things first, standardize our values so that we transform this from an X variable to a z-score. So we said to standardize, we take the z-score, which is equals to X minus mu divided by the standard deviation, provided this z-score follows a normal distribution with mean 0 and standard and a variation of 1. So let's standardize this. We'll end up with the probability. So if we standardize it, our X is transformed to a Z. So we have Z is less than 40. So let's standardize 40 as well. So we'll have 40, which is the X variable, minus mu, which is equals to 30, divided by the SD. So if the variance is 16, the standard deviation is the square root of 16, which is a value of 4. So this means you want to compute the probability that Z is less than what? What is that value? 40 minus 30 divided by 4, 2.5. So you want to compute the probability that Z is less than 2.5. So again, go back to your sketch. Have your sketch as follows. We have your 0.0 there, you have 1, you have 2, you have 3. So 2.5 is here, is there, and you want to get Z is less than 2.5. So we're interested in the left-hand side of it. So if you're interested in the left-hand side, this means that the value we'll get from the table is actually the probability we're interested in. Because again, we said the value from the tables gives us the the left side of the Z-score. So since this is a shaded area that you're interested in, we simply read the value of 2.5 from our table. So go back to the table and read the value for 2.5. 2.5, you have it here as 0.99379. 99,379. 99,379. So that's going to be your probability that P is going to be, your probability that X is going to be less than 40. I hope you can see the flow. I hope it's coming to us. The more we do it, the more we understand. Then let's look at one last example. So again, please refer to the notes. There's other questions there with solutions. So you can have a look at that and compare your answers. I hope I can get rid of it. So we do one last example. So we're told that family income is believed to be normally distributed, with a mean of $25,000, and a standard deviation of $10,000. We're told that if the poverty level is $10,000, what is the percentage of the population living in poverty? Then you are also asked, a new tax law is expected. To benefit middle income earners. A new tax law is expected to benefit middle income families. Those with incomes between $20,000 and $30,000. What percentage of the population will benefit from the law? So we have two parts to this question. Let's start with the first part. Let's understand the question. We are told that family income is believed to be normally distributed with a mean of 25,000 and a standard deviation of 10,000. So up to that point, you already know that's the variable in question. Let's call it variable X. Let's call it variable X. So let X be the what? Be the family income. And you're told that this same family income is believed to be normally distributed with a mean of 25,000 and a standard deviation of 10,000. So if the standard deviation is 10,000, then that means the variance is 10,000 squared. Because remember, for the notation, we denote using the mean versus the variance. So if SB is 10K, then variance is 10K squared. So we have that first line. Then we are told that if the poverty level is 10,000, what is the percentage of the population living in poverty? So anyone below a family income, or any family below a family income of 10,000 means that they're living below, or they're living in poverty. So they want us to compute this percentage. So what you're basically being asked for part 1, we compute the probabilities of the families living in poverty. This means you want any family income that is less than or equal to 10,000. So if you have anything less than or equal to 10,000, that means you're living in poverty. So what is this percentage that is living in poverty? So what that first bit is simply asking is the probability that X is less than or equal to 10,000. So once you have this probability formula, all you need to do is now first again standardize. So let's standardize this. To standardize, we'll end up with P into Z, because our X is transformed to Z, is less than or equal to what? For standardization, you're still using the same formula, whereby Z is equal to X minus mu divided by sigma, provided it follows a normal distribution with a mean of 0 and a variance of 1. So we'll have value of X here is what? Is 10,000 minus value of the mean, we are given as 25,000, divided by the standard deviation, which you're given as 10,000. So what will that give us? That gives us the probability from Z, which is less than or equal to 10 minus 25 divided by 10. This gives us negative 1.5. So we want to find this Z score. So again, if we plot this, what are we looking for? If this is my normal curve, I have 0 there. So this is 0, 1, 2. Then I have 1 and 2. I want to find the probability that Z is less than or equal to negative 1.5. So negative, this is negatives. So negative 1.5 should be somewhere here. So the probability that Z is less than or equal to negative 1.5, we want this shaded bit. So since this is the left-hand side, the probability will simply be equal to the value at negative 1.5 from our table. So we'll go back to negative 1.5. Go back to negative 1.5. Negative 1.5 here is 0.06681. 0.06681. So to answer the question, what is the percentage of the population living in poverty? So we simply convert this probability to a percent and confidently say that approximately 6.68% of the population is living in poverty. Very simple and straightforward. All you need to know is how to standardize and how to read the values from the table. So we get 6.68%. Then the second bit of the question, what are we being asked? We're told that a new tax law is expected to benefit middle income families, which are those earning between $20,000 all the way to $30,000. what percentage of the population will benefit from the law? So of course, we've already been told that whoever will benefit from this law are these middle income families. And you're told that these middle income families earn from 20,000 all the way to 30,000. So again, they're simply asking us to compute this probability. They're simply asking us to compute this probability. So how do we go about this? Step one, standardize. So standardize will have P into, what's the standardization for 20,000? Give me the value itself. Standardization for 20,000. Anyone with the standardization for 20,000? .5. Is it 0.5 really? Anyone else with a different solution, standardization for that? For the left-hand side, for the what? For the lower limit, standardization for 20,000, yes, negative. So you take 20K minus the mean, which is 25K, divide by the SD, which is another 10K. So this will give you negative 0.5 all the way to, now we transform it to a Z. We transform it to a Z all the way to, what about the upper limit? 30,000, if you standardize, what do you get? $30,000, standardize it. Waiting for the standardization of 30,000. Anyone on the chat box, standardization for 30,000? Someone has what? 0.5, yes. So we have from negative 0.5 all the way to 0.5. So how do we get this? Anyone seeing something? There's rule number 4 coming up here. Rule number 4, whereby we had probability of negative A all the way to positive A. All the way to positive A. How did you say we compute this? If the A is the same value and you're moving from a negative all the way to a positive value, then we are talking about twice the standardization for, not the standardization, the Z-score for A multiplied by 2 minus 1. So if you go back to rule number 4, this is what it stated. So what we need to do is get our Z-score for A. So let me project it and see if any of us can give us that value. What's our Z-score for 0.5? Go back to our table. 0.5 is direct. This one is easy to see. So we have it as 0.69146. 0.69146. So we'll have 2 into 0.69146 minus 1. So 0.69146 times 2 minus 1. This gives me 0.38292. So this is the probability of guys that fall within this particular range of income from 20K all the way to 30K. What was the question? What percentage of the population will benefit from this law? So percentage is simply what we have here. We convert it to a percentage to give us 38 point what? Approximately 38.3% of the population will benefit from this particular new law. So that's the form, another form in which the questions can be asked. So it's not always direct, where you're just told to compute this, compute that. No, sometimes you're given such scenarios. Yours is to evaluate and interpret it and give it as a probability, then standardize it. Once you standardize, have your plot for the normal curve, determine which area you're interested in, go back to your table for the z-scores, then again, have the 4 rules on your fingertips, then get your respective probabilities. If it's in terms of percentages, you simply just multiply by 100 to get your value. Yeah, so that covers normal distributions. That covers the normal distributions. So if you go back to the notes, I think there's just one. There's a couple of examples here, though I don't know which table these guys were using. Some of the values are really off. So use the tables. The table that I've been using, I've uploaded it on Moodle as well. So that we use our standard table so that our values are all similar. So there's exercises there you can look at and see how you compute. This one is used to help us with computing the probabilities. Once you understand how to compute a probability, then it can't be hard for a problem. So we've looked at example 1, look at this, look at example 2. We only did part A. So check out how you can get the probability for. I think I'd encourage you to attempt it first, then compare with what they have so that you're able to identify an area where you still need to go through it again. Same thing with part C, you can look at that. There's this example 3 as well. It's quite straightforward. That's why I left it out so that you can have a look at it. We've done example 4. Then there's an exercise as well with the different ways in which these normal probability distributions can be asked. So that covers what we need to cover under probability distributions, which also brings us to an end to our course units of probability and statistics. We've covered all that you need to cover. All that is left is for us to revise, do or attempt a cut 2. I'll set cut 2 out of 15. I'll upload it, when is it? Probably by Friday. I've seen the exams are beginning on 28th or 29th. So depending on the day I upload, whichever day I upload, but it won't be any later than Friday, so that you have exactly a week. You have the least, that is the least possible time of a week to attempt it. So depending, whichever date I post it, the deadline is going to be on 27th. So look at your timeline, look at your schedule and how you operate with other units. But for me, I'll expect my work by 27th. I've seen our paper is on the 4th of April. So I'll really try to mark your work so that you have it back before the paper, so that for something that you've done wrong, you can compare. If I'm not able to do that, I think I'll still share the marking scheme so that you're able to compare your solutions with the right ones to help with revision. So once cut 2 is going to be a working out cut as usual. Then assignment 3 will still be a multiple choice. So both of them will be up by Friday and both of them need to be attempted by 27th. So cut 2 will be out of 15 and the assignment, for the assignment you're left with 10 marks. So assignment will be out of 10, a multiple choice one. So I'll look for some 10 questions, each carrying 1 mark. Same thing as what you did with assignment 1 and 2. Then attempt that, then with that, I think we can confidently say that we'll meet in the exam room. Now, unless there's any question, concerns, clarifications that you might have, anything to do with what we've covered. So next week, maybe I'm thinking we'll see. I don't know if we can access Moodle, all of us. that time for the class, I'd love us to use it for the assignment so that we are done. That means I'll post the assignment, yes, by Friday or whatever. But then I can have the deadline to be on that Wednesday so that you can use the 3 hours for class to interact and attempt the assignment together or whatever. Then you submit during that hour. So depending, I'll see once I weigh the options and all, I'll communicate through your class rep. That is Dennis, then yeah, we can call it a semester. So I'll see you guys in the exam room if there's no other question. Swali lolote. Thanks for for your time, good lecturing, thank you. Question? Nothing. Okay, so we can call it a day then. Enjoy the rest of your evening.